All right, hi everyone. It's a delight to be back here at BITSS, and I'm really excited to share this econometric theory paper with you. When is p-hacking detectable? So I'm going to start by summarizing everything I'm going to say today in a single slide. Okay? So p-hacking, as some of you might be aware, is a questionable research practice that distorts the scientific record and statistical results. Now, there's a flourishing literature on different ways to look at a set of studies and to check whether or not p-hacking appears to be present on average within the set of studies. However, many of these methods have shown, many of the papers proposing these methods have shown that there are some cases where we know p-hacking is present, but the method fails to detect them, either in simulation or in application. Now, what I'm going to show you first is some bad news. The bad news is that there are some examples of severe p-hacking that we can prove are undetectable by any examination of the t-curve at all. One will never be able to develop a test that looks at the t-curve that could detect certain kinds of p-hacking. And these kinds of p-hacking are both severe and simple. They don't need to be very exotic. So that's the bad news. The good news, not quite a solution, I guess, but the good news is that I can also propose a new way to look at a set of studies and check for the presence of p-hacking, a new test that I'll call the projection test that is consistent against all forms of p-hacking that are detectable. So if a form of p-hacking is detectable and your metadata set is large enough, this test will eventually detect the p-hacking in that case. How does the test work? The test will reject the null hypothesis of no p-hacking when the histogram of t-scores cannot be explained without resorting to selective reporting. This means that if you look at the histogram of t-scores, there's no way to produce a histogram like that without some sort of selective reporting. That's how the method will work. Other methods look at specific features of the t-curve. Instead, we're going to look at the entire t-curve all at once. Now, is the method useful? Is it an econometric curiosity, or can it actually be used? Well, in an application, I'll find that the method can detect p-hacking in some famous cases where most other methods could not detect any, and I'll show you an example of a simulation where even with a very large meta-study, the standard techniques for checking for p-hacking fail to find p-hacking, but this projection test can find it. So let's get started. What is p-hacking? I probably don't need to define it for this audience. I'm going to call p-hacking running many hypothesis tests and selectively entering the statistically significant results into the scientific record and leaving other results out of the scientific record. I probably also don't need to make the case to this audience that p-hacking is bad because it is. And it's bad because it is misleading. And it's misleading because the audience doesn't know what results were left out of the scientific record. There's plenty of evidence, which I'm sure this audience is familiar with, that p-hacking is a pretty common process. For example, Franco et al., which was cited earlier, followed more than 200 well-powered studies from the grant proposal to the publication stage and found that statistically strong results were significantly more likely to be written up than results that were not statistically significant. I probably also don't need to argue to this audience that p-hacking is consequential and probably has an impact on the conclusions that we draw across the social sciences. It may be a strong contributor to observed low replication rates across the social sciences. Okay. Now, why would we test for p-hacking? Why is it important to develop tests where we look at a set of studies and try to determine whether we can find evidence of p-hacking in them? Well, there's been a number of reforms and a great deal of additional awareness since the Franco et al. Was published across the social sciences. This gathering is evidence that people care about research transparency and about detecting and remedying p-hacking and publication bias. question that we might ask is, how effective are we being? Can we monitor whether or not the prevalence of these questionable research practices is on the decline. Now, the first best solution is replication and reproduction. So obviously, reproduction would be the best or a better way to check whether or not p-hacking is present in the literature. However, although it's first best, replication and reproduction can be very time-intensive, even with the assistance of AI. And it could also benefit, for this reason, we could benefit from a little bit of targeting, right? Try and target certain literatures that might be where we might want to put more of our replication and reproduction efforts. So enter the p-hacking test, right? If we examine the histogram of published t-scores or p-values, this can reveal certain literatures where p-hacking appears to be more common than others. And I'm suggesting to you that this might be one way to help target our efforts. I'm also going to caveat this. I'm not going to try to tell whether any individual test or paper was p-hacked, but rather to evaluate an entire literature all at once for the prevalence and impact of p-hacking on average within a large literature. Okay, so let's look at an example of this. Can we examine the t-curve and tell whether or not something is wrong with it? So I generated this, for ease of illustration, I generated this t-curve using simulation. And you can probably tell that from this histogram that something is wrong with this t-curve. There appears to be a spike right around the statistical significance threshold of 1.96. You can tell as we approach 2, suddenly we jump up in the histogram. There appear to be some missing t-scores to the left of 2. And you can see that right here. This kind of p-hacking is easy to detect. And there's a well-known set of tests that will detect p-hacking that produces a histogram of t-scores like this one. So you can see in principle, let me just go back. Back is not working. Okay. You can see that in principle, one can examine the histogram of t-scores and determine whether or not something is wrong with it. Now, Brodeur et al. Published a very influential paper in 2020 where they find greater evidence of p-hacking in observational studies than in experimental studies in economics. Now, responding, Yuri Simonson published a really wonderful blog post that points out that there are a couple of problems with testing for p-hacking, and we're going to be really digging into those problems today. The first problem that Simonson's pointing out here is that it's actually quite easy to generate very suspicious-looking t-curves without any p-hacking in them. It's easy to make a suspicious-looking t-curve that's actually honest. On the other hand, it's also possible to do the opposite. It's possible to produce a t-curve where there's a lot of very severe p-hacking that nevertheless looks innocent. So these are two challenges with testing for p-hacking. Finally, Simonson makes a hypothesis or a prediction. And the prediction is that the sort of p-hacking that happens in experimental studies is probably harder to see than the sort of p-hacking that he thinks happens in observational studies. I won't get too much into the details of that. I'll refer you to his blog post for that. We're going to return to this prediction at the end of this presentation, so keep that one in mind. But first, we're going to examine more carefully these two challenges for testing for p-hacking by looking at a histogram of t-scores. First, I'm going to show you an example of a t-curve that looks suspicious but is in fact innocent. So for this t-curve, I generated it by simulation without any p-hacking or selective reporting at all. Nevertheless, you can see that around the significance threshold of 2, to the left, there are relatively few t-scores, and as we move to the right, there's more t-scores. This t-curve was generated simply by researchers who were doing good power calculations. So many of the t-scores happen to be significant because their power calculations were good. But this is completely honest. There was no selection involved, even though the t-curve looks suspicious. On the other hand, and this is a little bit more distressing, Some histograms of t-scores are the outcome of really severe p-hacking, but they look innocent. And this is one of the points I want to stress today. So for this t-curve, I generated it by having every researcher draw 8 t-scores that are correlated with one another, and then they only report the largest one. So this is very severe. I ran 8 tests, and I'm only telling you about one of them. I've misled you by only telling you about one of them. This will generate the following t-curve, okay? Now, it's also possible to generate the exact same t-curve using a different simulation process that doesn't include any p-hacking or selective reporting at all. In this scenario, everyone reports every t-score that they draw, but the distribution of true intervention treatment effects in that literature is different. And it's different in such a way that the histogram of published t-scores looks exactly the same. So you can see that these are the same t-curve, and we can mathematically prove that they are actually the same. It's not just that the simulations look similar. These t-curves are identical in population. So this is a bit disturbing because it means that there are some forms of p-hacking that always have an alibi. They always have an alibi. So let's return to Simonson's 2 challenges. It's easy to generate suspicious-looking t-curves, and many p-hacking strategies produce guilty t-curves that look innocent. Now, there's been a lot of econometric theory, statistical theory, that addresses challenge number 1. For example, Elliott et al. Addressed challenge number 1 by developing 5 valid tests for p-hacking that check for specific restrictions or specific shape distortions in the t-curve. And these, it's impossible to make them find p-hacking that isn't there. They're what we call valid. However, they have a problem, and that's that their own simulations in these papers, in the original papers that proposed the tests, these simulations show that their tests can't always find p-hacking, even when we know that it's there. And they often fail to find it in empirical examples where we're pretty sure there was at least some selective reporting. This leaves challenge number 2 unaddressed. And so I want to address and think about challenge number 2 with you today. So here are the research questions I'm going to try to answer. What kinds of p-hacking are detectable by examining the t-curve? Examining the t-curve is not the best way to check for p-hacking, but it's by far the cheapest and most scalable and can help direct more serious efforts like the ones we just saw. Question number 2, are there forms of p-hacking that are detectable in principle but not picked up by the standard tests? There are. And if so, how are we going to be able to detect those hard to detect but ultimately detectable forms of selective reporting? So to answer these 3 questions, unfortunately, I will need to set up just a little bit of mathematical notation. I've hidden most of it. But let's just formalize a few things so that we can all speak the same language with each other. So consider a population of t-tests. Each researcher draws an unobservable true effect H. This is like the true effectiveness of the drug being tested or of the intervention. Researchers don't observe the true effect. Instead, they observe the t-score. The t-score is the true effect plus some sampling error, where the sampling error has the standard normal distribution. The insight here is that if there is no p-hacking, the histogram of T must be smooth. It must be as smooth as can be. It can't jump up and down. It can't be discontinuous. It can't have kinks. It can't have 3rd or 4th order kinks. It has to be very smooth. What does that mean? It means that there are only so many t-curves that are even possible to produce honestly. Not every histogram that you can imagine is possible to produce using this model. And what we can do in principle is check whether the histogram of t-scores that we observe is close to the set of t-curves that would be possible if the t-score was the sum of a true effect plus noise. So this brings us to the question of detectability. Is it possible to fool such a test? And the answer is yes. Elliott et al. Point out that their tests are unable to detect some kinds of p-hacking, but it's unclear why. They don't offer an explanation as to why. They just are very honest, and they document that it's possible. They don't say why. Okay? Here's the harsh reality that I'm going to acquaint you with. Some combinations of 1, a p-hacking process, and 2, a distribution of true effects yield a hacked t-curve that looks like an unhacked t-curve for a different distribution of true effects. In other words, you can get a hacked t-curve that has an alibi. I'm going to call p-hacking undetectable if it produces a t-curve that's got an alibi, a t-curve that could be explained without p-hacking. If p-hacking is undetectable, it must and will evade all valid methods that are based on the t-curve alone. So how can p-hacking be undetectable? How is that even possible? I showed you a simulation. Let me demonstrate to you in symbols and math how this is even possible. And the example is really very simple. So let's consider 2 cases. In case 1, a researcher draws 2 independent t-scores with the same true effect, and then they're going to report only the larger one. So they're p-hacking. They are hiding one result and just reporting the more exciting result. Okay? In this case, the t-score is distributed as the sum of the true effect plus the maximum of 2 noise variables. Okay? This p-hacking process will be undetectable if we can find another way to produce the same distribution for the t-score honestly. I'm going to produce the same distribution honestly. And it's so simple, it's going to look a little silly after I've done it. So all we have to do is relabel what's noise and what's a true effect. So here's the alibi. In case 2, a researcher will draw 1 t-score and always report it. So no p-hacking here, completely honest in case 2. In case 2, but the difference is that in case 2, the distribution of true effects has a different distribution, a different shape. The true effects are distributed as the maximum of 2 normals. Now the noise is just distributed as a normal on its own because there was no p-hacking. So what has happened? What's happened is that I've produced another distribution of the t-score that is the same without any selective reporting. I've produced an alibi. So this proves that the first p-hacking situation with a normally distributed true effect and a researcher who reports only the maximum of 2 t-scores is undetectable. You'll never be able to verify that p-hacking occurred in this situation because that t-curve has an alibi. Okay, so this is a distressing example. It shows that we won't always be able to detect p-hacking when it's there. Okay, so now let me answer the question that I pose in the title of the talk. When is p-hacking detectable? It's detectable when it makes the distribution or histogram of t-scores non-smooth. So I've provided you 3 examples here. The red curve is a curve where there was p-hacking, and it's easy to detect. Why is it easy to detect? Because the t-curve has a kink. You can see that a little past 1, the t-curve has a corner. That's pretty non-smooth and could never have been produced honestly. The second t-curve also turns out to be detectable. It isn't quite smooth enough to possibly be produced without selective reporting, but it's not obvious to the naked eye. It's not obvious to the naked eye. The solid blue line is pretty smooth, but it turns out mathematically it's just not smooth enough to have been produced without p-hacking. So we would call this hard to detect. And finally, the dashed line is a fully undetectable set of p-hacking. The p-hacking is present, but it has not produced enough non-smoothness in the p-curve, and it does have an alibi. Right? So p-hacking is detectable when it makes the t-curve non-smooth. Okay, so now the question is it possible to come up with a test that will detect p-hacking whenever it is present and detectable? And I'm going to propose such a test to you right now. Okay? So the meta-analyst's null hypothesis is that no detectable p-hacking occurred. And here's how the test is going to work. I don't have time to delve into things like the singular value decomposition or regularization or any of those other technical topics, but instead I'm going to visualize how this test works with a picture. The goal of the test is to look at the t-curve that we observe, the red, which is symbolized by the red dot, and then to look at the set of all possible t-curves we could produce honestly and find the closest one to the observed t-curve. So we observe a t-curve and we find the closest honest t-curve. We're going to conclude that p-hacking is present when the distance is too large to be explained by noise or by random chance or by rounding error or by the fact that the t-score is really distributed t and not normal. If the distance between the observed t-curve and the set of all honest t-curves is too large, then we conclude that there was p-hacking present. This is the visualization of how it works. It's very painful and long to show that this all works. You can see the paper on arXiv for that, but this is the visualization of what we are doing. Okay? So let's demonstrate that this thing has some usefulness. First, we're going to demonstrate it with a simulation, and then we're going to go to some real metadata. So first, I'm going to do a simulation where p-hacking is nearly undetectable. What do I mean by nearly undetectable? It's very close to a p-hacking process that I know is undetectable, but it's not quite there. So in this situation, a researcher draws 8 independent t-scores from the same distribution of true effects and reports the largest one. So they're really p-hacking a lot. They've picked 8 they've run 8 regressions, and they're reporting the most exciting one. And this is really bad. It distorts the size of the t-test from 5% to 33%. So this is really not transparent. In this case, even with a metadata set of 100,000 independent studies, all 5 tests proposed in Elliott et al. Find nothing. You can see that on the bottom row of this table. When there is p-hacking, the Elliott et al. Don't find any. Only in 5% of simulations do they detect p-hacking, which is what you would expect if there wasn't any p-hacking at all. Whereas the projection test that I just showed you finds it every single time when there's 100,000 studies. So we've demonstrated that in principle, there are some kinds of p-hacking that the standard tests, like the binomial test or the caliper test, cannot find, but the projection test can. Now let's look at the data. So I'm going to turn to a classic meta study, which has already been cited today. This is the Brodeur et al. 2020 Methods Matter data set, which includes almost 22,000 t-scores. These t-scores correspond to main hypotheses only. They don't include like robustness checks or constants or things like this. And they're separated into 4 different methods, the same methods that we saw in the last presentation: RCTs, RDDs, DIDs, and IVs. So what do we find? We'll find that the projection test, its p-value is in the 4th column, finds p-hacking in RCTs, IVs, and DIDs. However, none of the 5 tests in Elliott et al. Find any evidence of p-hacking in any of these subsamples of the Brodeur et al. Data set. What's this saying? What does it mean? It means that there's something wrong with the t-curves for RCTs, IVs, and DIDs. Something is distorted about those t-curves, but the distortion is not of a character that the Elliott et al. Tests were looking for. It might be a distortion that looks like it might have an alibi, but it doesn't, and we need to formally test to really check whether that distortion has an alibi. This evidence, in particular, I want to notice that the evidence against the null of no p-hacking is strongest for RCTs. And this evidence kind of favors Simonson's hypothesis that he posted on Data Colada 6 years ago, that there might be p-hacking that occurs in RCTs that is harder to see or harder to notice in the t-curve than for other methods. Right? I'll also notice that there are other working papers that also find p-hacking among these tests. I'm not the only person to have found it. All right. There's some caveating here. I'm going to skip this for time. Well, maybe I actually have a few minutes. Let's not skip it. You might have some quibbles. 5 minutes, great. You might have some quibbles. You might say, well, Stefan, in your model, the t-test was distributed normally. In reality, the t-test t-score is distributed t. Is that going to mess up your test? Is that going to make the t-curve look more distorted than it really is? And the answer is yes, but I can account for that, and I do, and you should see the paper. Another example is, well, what about rounding and derounding? When t-scores are rounded, they can produce spikes, for example, at the value of 2. That's going to look suspicious, but it's just coming from rounding. So the solution, a typical solution, is to deround the t-score. And you might quibble that, hey, how exactly does derounding work? Is it going to make the t-curve look distorted to my statistical test when really it's just derounding that's causing the distortion? And the answer, once again, is we can adjust the critical value of the projection test to account for rounding and derounding as well. So what I'm saying is that the distortions that we observe in the RCT and DID t-curves cannot be explained by resorting to rounding and derounding or to the fact that t-scores are really distributed t and not normally. Okay? So let's wrap up. What have I said today? P-hacking is known to be pervasive and can be very hard to detect, and it can be useful to monitor different literatures at scale using tests for p-hacking. This paper, to my knowledge, and please correct me if I have been preempted here, documents the first concrete examples of severe p-hacking that we can prove cannot be detected by any examination of the t-curve. It proposes a new projection test that can't be evaded by any detectable form of p-hacking and demonstrates that the projection test is useful because it finds p-hacking in simulations and real-world data sets where other tests cannot find anything. Thanks very much.
Thanks. Looking and listening to your paper, it makes me think of like specification curves. Is there any analog to your test in how I should think of specification curves as like an empirical idea surrounding?
Define that for me.
A specification curve?
Yes.
Like a handful of different robustness checks you might perform across multiple dimensions and the interaction of those dimensions. So you could think of a 2x2 specification curve would be 4 different specifications interacting all of the first 2 with all of the second 2 dimensions. And you could do this across a broad spectrum.
I see. So what you're thinking of is, can we put a restriction on the way the specification curve looks? And if that restriction is not met, then we would conclude that something is distorted, that there was some selective reporting going on. Is that what you're saying?
Or if there's an empirical analog to your test.
Yeah, so the thing is, the test relies on the fact that we are looking at many studies, and these studies are independent of one another. Within a study, t-tests, statistical tests, can be correlated in any exotic way that you can think of because they come from the same data. So what this test needs is it needs the t-curve to be composed of many studies that are each independent of one another. You could map a very specific quantity, which is how far away is the observed histogram of t-scores from the closest honest histogram of t-scores. Now, does that correspond exactly into the severity of p-hacking or how bad the p-hacking is? That would be a subject for a great deal of thought, and I don't have an answer for you. But you could map over time the change in severity by looking at the distance from the observed histogram to the closest honest histogram. I haven't done it, but you could.
So over here. So super interesting that it's like the next logical step in my mind is try to understand what fraction of the universe of p-hacking can be detected. What fraction is, you have 3 categories, right? The easily detectable, the hardly detectable, the impossible to detect. So it will be, how would you think about even getting a rough measure of how much can be detected by these new tests. That's like the first thought, but it's kind of like an empirical question that it's hard. The second one is that the Brodeur data, they have these 20,000 estimates. I would be careful in terms of thinking of main estimates. Yeah, basically it's roughly like 60 tests per paper. A paper doesn't have 60 main hypotheses. So I think it's a challenge to start thinking of like what is an actually main estimate.
Certainly. So Brodeur et al. In their paper, they say that they're all main estimates according to their criteria. So they're not like completely auxiliary estimates. But I agree, what counts as a main estimate, we can be much more selective about. Now, because I was afraid of temptation, I have not tried this on any other subsamples other than what I have shown you, right? So I haven't, since it's a methods paper, that would be for future work. But certainly once the code is published, we can start looking in more detail and chop things up more. I was frankly afraid to do it.
So just to clarify, I should think of this as in the best of all possible worlds, we still detect p-hacking with that set of data.
I'm saying I want you to be innocent. You are innocent until proven guilty. I'm going to find the closest honest T-curve to what you gave me. And if I can't do it, I have to conclude that there's a distortion here that just can't be explained. That's how the test works.
So is this a lower bound on the worst possible world?
Yeah, it depends on what you mean. But yeah, we're being very charitable here. We're finding the closest honest T-curve to the one you gave me. We want you to have an alibi. We're going to try to find you one. If we can't find you one, we conclude there's p-hacking. And that's what happened in the Brodeur et al. Metadata.